Just gonna do the typical check. Can I hear myself? Yes, I can. Cool. All right. So today I just want to do a very light episode because I am tired, but I would like to go over some of the stuff I learned last time, which is trying to figure out how these chemical formulas work. I was looking at the periodic table, just understanding it a bit more. Um, I think I covered condensed formulas, Lewis structure, skeletal formulas, so I'll go back through those. And this is all in an aim to understand how to draw the chemical formulas myself, and I'm going to practice on the nucleic acid, which is the DNA um, bonds. So yeah, that's what I'm going to do, and I'm going to start, which I think I'll do from now on, with a Duolingo lesson because it's Greek, and apparently everything in chemistry and maths is Greek. So here we go. Ze. I don't know what that means actually. Ze. Maria the rice. So it's the R is the P. Maria. To is the, and rice is uh it's probably this one, but it might be that one. Anyway, that's Ros or Rosie, I guess. Rosie. Risi. Okay, so this brings it up. Risi. Okay, that makes sense. Zo. Yeah. The pink mini market. Let's start with the to pink. I don't know. Pause. Peasy. Maybe that one. Risi. Peasy. Ah, you see, it's that time of the day. Mini. Let's see. This is an N. So, and this is the M. Mini. That sounds good. And market. Market. Let's see what pink was. Oh, I was wrong. Okay, cool. Nice. Do rose mini market. Do rose mini market. I can't say it like she's saying it. It's wonderful. Z. The pink carrot. To. Oh, rose. That makes sense. Rose. Okay. Do rose carroto. Okie dokie. Thanks, dude. Maria, the rice. Oh no. Don't need the keyboard again, do I? Ah, keyboard. Let's see if I've got this open. Oh yeah, here we go. So, Maria, I guess, will be this, but that might be an M. Yeah, okay. Ma, and then it's P is the R. Mari. Yeah. To. And rice was resi, so it's re. See? I don't think that's right. Ah. Oh yeah, because it's got that funny thing. Haha. We did know that. Dear me. Oh yeah, and I don't know how to do the funny little accents, but oh well. Guess it's that. Maria to Rizzi. Rizzi. Alright, cool. Perfect. That sounds good. Okay, so let's go back to that. Take that away. And close this down. Right. Where do I start? I think I had some questions at the bottom. Yeah, what we want to do next episode, continue reading this wiki, try and draw some of the components of the nucleic acid. So that's exactly what I went over at the start, so that makes sense. Let's go and do that. Okay. Just got to find the wiki article now. What was it again? Structural formula. Oh yeah, it's here. Okay, cool. So what we're going to do, I think, just recap these pages. We've got the periodic table, awesome. Cytosine, cytosine, cytosine. I don't know what that means. Cytosine is one of the four main bases found in DNA and RNA, along with adenine, guanine, I don't know, and thymine. I should probably learn how to say these. Uracilin RNA. It is a pyrimidine derivative. That's interesting. I know what derivative in maths is. I guess it has no correlation at all to that. It is a derivative of that with a heterocyclic aromatic ring. Aromatic? Okay, right. Okay. We're going to have to figure out some of these. So first of all, how do you say this? This is ridiculous. How do you say adenine? Adenine.
Adenine.
Adenine. Okay. So let's imagine. Oh. Adenine. Guanine. Guanine.
Guanine.
Guanine. Thymine. Beep. Thymine. This one. How do you say this? Do you say
Uracil.
uracil? Okay. So Dean, adenine, guanine, thymine, uracil, pyrimidine. Let's just check this one as well.
Hey guys, Molly May here.
Not adverts. Ah. Okay.
Pyrimidine.
Pyrimidine. Okay, that's a nice word. Okay, what the hell are these? So, cytosine is one of the four main bases found in DNA, along with these other ones: adenine, guanine, thymine, uracil, pyrimidine derivative. Oh, it is a pyrimidine derivative with a heterocyclic aromatic ring. Ah, this can't be right. Aromatic.
Aromatic.
That can't be right. Aromatic. Chemistry. Aromatic compounds are the unsaturated compounds having one or more planar rings of atoms with alternate single and bonds. These compounds have unique stability known as aromaticity. The word aromatic means odorous. Wow, it does. Alright, fair enough. Many aromatic compounds have an odor, but not all odorous compounds are aromatic. Very interesting. Okay, so it is a pyrimidine derivative with a heterocyclic aromatic ring. Yeah, okay. And two substituents attached. An amine group at position 4 and a keto group at position 2. Here. Amine group at position 4. NH2. So let's see what amine is. There you go. The substituent NH2 is called an amino group, and a keto group at position 2. This O. Let's have a look at this. R2C equals O. In chemistry, a ketone is a functional group with the structure R2C equals O. Oh, is this bound? Double bond O. Okay. R2C with a double bond of O. Maybe. Where R can be a variety of carbon-containing substituents. Ketones contain a carbonyl group. Carbonyl. Oh my god. Wow, this is so much harder today. A carbon-oxygen double bond. Okay. The simplest ketone is acetone. R equals R prime. So is it R double bound to R prime? Double bound to methyl? I don't know. With the formula CH3C, and that's, I remember that. That's because the C doesn't bind to the, I can't remember what that was now. This one though, this is condensed formula. Yeah. It's because the next character doesn't bind with the C or something. Oh, I can't remember. The next character doesn't bind with the C. Maybe not. Many ketones are of great importance in industry and in biology. Examples include many sugars, ketosis, many steroids, testosterone, and the solvent acetone. Cool. Right. The nucleoside of cytosine is cytidine. In Watson-Crick base pairing, it forms 3 hydrogen bonds with guanine. I didn't get a lot from that. Oh well, let's come back to that. So a ketone in chemistry, a ketone is a, yeah, we just read that. Okay. Actually, you know what? I didn't read that. Undo close tab. Amine. In organic chemistry, amines are compounds and functional groups that contain a basic nitrogen atom with a lone pair. Okay. Primary amine. Amine? I can't remember now. Secondary amine. Triple amine. I have to do it. I'm so sorry. I know I just looked it up. I know. How do you say amine? Amine. Okay. Primary amine, secondary amine, tertiary amine. Okay. What is that trying to say? Double bond with what? I can't remember how that works. Yeah, this is perfect then. So going back over the last stuff is going to be absolutely crucial. So amine are compounds and functional groups that contain a basic nitrogen atom. Here it is, with a lone pair. In chemistry, a lone pair refers to a pair of valence electrons that are not shared with another atom in a covalent bond, and is sometimes called an unshared pair or non-bonding pair. Okay. Excuse me. Okay. Yep. So this is the one we want to keep open. Natta projection. The Natta projection is a way to depict molecules with complete stereochemistry. Stereo means hard chemistry or stiff or something like that. What does stereo mean again? I can't remember. Define stereochemistry. Strong? Something like that. The branch of chemistry concerned with the three-dimensional arrangement of atoms and molecules and the effect of this on chemical reactions. Stereochemistry, a subdiscipline of chemistry, involves the study of the relative spatial arrangement of atoms that form the structure of molecules and their manipulation. And yet, I think the etymology was quite helpful for this as well. Solid, yes. Stereos, solid. Okay, fine. Um, so skeletal formula is what we've just found now. So the Natta projection is a way to depict molecules with complete stereochemistry in 2 dimensions in a skeletal formula. Depict molecules with complete stereochemistry in 2 dimensions. I'm going to have to read this properly. Stereochemistry is a subdiscipline of chemistry. Involves the study of the relative spatial arrangement of atoms. Involves the study of the relative spatial arrangement of atoms, okay, that form the structure of molecules and their manipulation. The study of stereochemistry focuses on stereoisomers, which by definition have the same molecular formula and sequence of bonded atoms, constitution, but differ in the 3-dimensional orientations of their atoms in space. But differ in the 3-dimensional orientations of their atoms in space. For this reason, it is also known as 3D chemistry. The prefix stereo means 3-dimensionality. Ah, that's really helpful. Hey, nice. Wow, this poor word. An important branch of stereochemistry is the study of chiral molecules. Stereochemistry spans the entire spectrum of organic. So I don't really get an intuition yet. I hope you don't mind. I'm going to read it one more time. The study of the relative spatial arrangement of atoms. Relative spatial arrangement of atoms that form the structure of molecules and their manipulation. Let me just read this again. Is a way to depict molecules with complete arrangement, 3D, 3-dimensionality. Okay. Oh, oh, I see. So this is where. Okay, so way to depict molecules. Okay, so when they're in the 3-dimensionality, it's a way to depict them in 2 dimensions in a skeletal formula. Okay, that makes sense. This concept is named after Giulio Natta, Italian chemist and Nobel laureate. He won a Nobel Prize in Chemistry in 1963 with Carl Zeiger for work on high polymers. In a hydrocarbon molecule, with all carbon atoms making up the backbone in a tetrahedral molecular geometry, the zigzag backbone is in the paper plane. Chemical bonds depicted as solid line segments. So this, with the substituents either sticking out of the paper toward the viewer or away from the viewer. This, I guess. Chemical bond depicted as dashed wedges. Oh, dashed wedges, okay. Cool, okay. Meta projection. So that's a thing. Cool, good to know. We know that now. Um, this is what we are going to learn more of, so I'm going to close it now. Valence electron. In chemistry and physics, a valence electron is an outer shell electron that is associated with an atom. So let me just try and draw that. If I remember correctly, I don't think I do. We have the middle with the protons, and then we have the can't remember what these are. Neutrons, are they? Can't remember. And then you've got the electrons on the outside. It says is an outer shell electron, so this, that is associated with an atom. An atom. And that can participate in the formation of a chemical bond if the outer shell is not closed. If the outer shell is not closed in a single covalent bond. chemical bond that involves a sharing of electron pairs between atoms. Both atoms in the bond contribute one valence electron in order to form a shared pair. So electron from hydrogen and electron from carbon, 4 covalent bonds because they're sharing the bond. I see, okay. So it's like if there was one here that it's using both of them to make that bond. Hmm. Okay, well, that's fine. Okay, isopropyl alcohol. Oh, this is when I was trying to get those symbols up. OH, okay. Ethanol, that's CH3 uh CH2 OH. CH3 CH2 OH. Oh yeah, we win. Chemical markup language. Oh yeah, that's right. You can form chemical markup in like XML. That's kind of cool. What else did we learn? International Chemical Identifier is the EU pack. EU pack. Alright. Simplified Molecular Input Line Entry System. Whoa, smiles. Simplified Molecular Input Line Entry System. Specification in the form of a line notation for describing the structure of a chemical species using short ASCII strings. Okay. Oh, excuse me. Isomeric. Um, Isomers are molecules or polyatomic, poly means many, many atomic ions with identical molecular formulas. That is, same number of atoms of each element, but distinct arrangements of atoms in space. Isomerism is existence or possibility of isomers.
Enantiomers.
sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Now for potassium. See an equation for the... All the alkali metals react with water in the same way. Let's see an equation for the reaction. The reaction is a bit more vigorous. All the alkali metals, although the reaction... The same sort of thing happens, although the reaction is in gas. We'll start with lithium. Floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same equation for the This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal. There are six and
I've been talking without my thing on all the time. That's a shame. Oh well. Well, just to recap with the last one. I've been talking without my thing on all the time. Just to recap with the last one, it's not that important. I was figuring out what the formula was, and I found out that the yeah. Let me just go over it again. Oh, so annoying. I'm so sorry. Have I got it on there? Yeah.
the same sort of
classic first mistake of recording. So this 2 sodium and 2 water gets converted to this, and you've got this H2 gets moved from here, and one of them is shared with this and binds to the sodium, and the S is solid, L is liquid. I don't know what this means, and then this is gas. So that was the breakout. That's literally all I was doing in that last part. And I'm moving on to this one now. So, oh, and I also tried to work out what was it cesium? Yeah, cesium reacts with water, so it would be something like this essentially, I think. Um, yeah, okay. Something like this because you've got the 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 two. I don't know why there's two. I have no idea why, but there's cesium and that's the solid. Then you've got the H2O, it's a liquid. So you've got the two cesium bonds to the O and the H, but one is released as gas, or this is released as gas. Yeah, and the bond happens, so that's where the other H has gone. Okay, cool. Oh, I'm so sorry, guys. Let me just make sure I'm yeah, cool. Okay. So okay, the alkali metals. The elements in group 1 are known as alkali metals. They react rapidly and they make alkaline solution. Okay, and hydrogen gas. Halogens. The element in group 7 are known as halogens. Fluorine and chlorine are gases. Bromine is one of the only 2 liquid elements. Let's read that again. I'm so annoyed that I muted myself. The elements in group 7 are known as halogens. So let's go and have a look at that. Here's 1, 2, 3, 4, 5, 6, 7. Here they are. Fluorine, chlorine, bromine. Okay. Fluorine and chlorine are gases. Bromine is one of the only 2 liquid elements. Iodine is solid. They exist as diatomic 2-atom molecules. They have 2 atoms in each molecule. As you go down the group, the halogens become less reactive. Noble gases. The elements in group 0 are known as noble gases. They are very unreactive and exist as individual atoms, monatomic. So noble gases are group 0. Wait, what's group 0? That's interesting. Group... There isn't a group 0. 10 maybe. That can't be it. Ah, you let me down, guys. Noble gases. Noble gases. Let's see what one is. Helium. Let's say He. This. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it means group 18. Let me just do that. Yeah, fuck it, whatever. Okay, so the transition metals are elements which are found between groups 2 and 3. Transition metals are elements which are found between groups 2 and 3. Well-known examples are iron, copper, and gold. They are generally quite dense, and many form brightly coloured compounds. Transition metals in group 2 and 3. 2 and 3, but Fe is iron, so I'm so confused. This is clearly just wrong. Well-known examples are iron, copper, and gold. Okay. Each element has its own atomic number. So sodium has 11. Let's just make sure that's right. Sodium would be Na Sodium is a gas, so it's not going to be here. It might be over here. Or over to the left. Oh, there it is. Sodium, oh god. Right, let me try that again. Sodium is, yeah, atomic number 11. The atomic number of an element tells you how many protons that element has. So let's just try and draw that. Na is going to have 11 protons. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That means it's going to have 11 electrons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And it's going to have some number of neutrons. So 11 negative electrons to cancel the charge from 11 positive protons. Electron arrangement. The electron arrangement of all atoms can be found in the data booklet. All the electrons are arranged into energy levels. These energy levels can only hold a certain number of electrons. The first energy level, the one nearest the nucleus, can hold a maximum of 2 electrons, with the others being able to hold up to a maximum of 8 electrons. Only true for the first 20 elements. So a sodium atom contains 11 electrons orbiting a nucleus in 3 levels, 2 in the lowest, then 8, then 1. So do I get that information here? 2, 8, then 1. Don't think so. Let's go here. 2, 8. Uses and properties. Let's have a look. Atomic data. Ionization energies. First, second, third, fourth, fifth, sixth, seventh, and eighth. Okay. States and isotopes. Nope. Okay, that's not so helpful. So sodium has 11 electrons. The first 2 fill the innermost energy level. The second energy level is also full, holding 8 electrons and 1 electron, remaining in the outer energy level. Wow. It is the number of outer electrons that give an element its chemical properties. This is why elements in the same group of the periodic table have similar properties. I see, so because sodium only has 1 exposed, then that's going to give it this kind of sub-reactive thing, whereas I guess Caesar has probably quite a lot to react with. I don't know. I wonder as well, 1H, 2H. I'd love to know what they all mean. Okay. The mass number is given at the top left of the element's symbol. For example, sodium has a mass number of 23. We know that the atomic number of sodium is 11. This tells us that sodium has 11 protons, and because it is neutral, it has 11 electrons. That makes 22. The mass number... Oh no, hang on, because one of these doesn't have a mass. I can't remember which one it was now. Let's see. The mass number... Yep, okay. Because it is neutral, it has 11 electrons. The mass number of an element tells us the number of protons and neutrons in an atom. The 2 particles that have a measurable mass. Okay, cool. Sodium has a mass number of 23 atomic mass units. Since sodium has 11 protons, the number of neutrons must be 23 minus 11 equals 12. That makes sense. Examples. 24 is the mass, 12 is the atomic number, and this 2 plus is going to be the neutrons. No. 12 is the protons, so 12 protons. That means there's going to be 12 electrons. That's 24. It's magnesium, so 24 is the mass number. Yep. Protons is 12. Neutrons is 12. Oh, because it only corresponds to mass. Yeah. Okay. I see. I see. I see. I see. Potassium has 39. So, yeah. Okay. I understand. Isotopes are atoms with the same atomic number but different mass number. Oh, okay. That's interesting. So, excuse me. 3, 11. So this, I don't understand that. These two carbon atoms are isotopes. Each has the same number of protons, but a different number of neutrons. Yeah, okay, that makes sense. Because, yeah, because this would be 6 protons, 6 electrons, and the rest would equal the neutrons. Elements are made up of isotopes, so the mass given in the data booklet is called the relative atomic mass. The relative atomic mass of each element shown in the data book is calculated from the masses of all the isotopes of an element, taking into account the percentage proportion of each. Example, there are 2 isotopes of chlorine. So this is 17 protons, 17 electrons. Excuse me, my maths is very bad. 17 times 2 is 34, so there's 1 neutron. And then this one is, yeah, 3 neutrons. So since the relative atomic mass of chlorine is 35.5, chlorine 35 must be more abundant because its mass number is closer to the relative atomic mass. I didn't understand that. Elements are made up of isotopes, so the mass given in the data booklet is called the relative atomic mass. Let's go and look at that again. Sorry, I'm trying to figure out. Ha! Um, Trying to figure out what this is going on about. Elements are made up of isotopes, so the mass given in the data booklet is called the relative atomic mass. Oh, okay, so it's different groupings for different things. So periodic tables, groups. BBC again. That's worrying. They only seem to have BBC links there. 0. That's interesting. So it must be like a stripped down version of it or something. 0 group in periodic table. The noble gases. Because mine is H. Oh, it is here. So but that's group 18, which makes a lot of sense. Why is it called group 0 rather than group 18? If the rest of the periodic table, the number of the group is the same as the number of outer shell electrons in the atoms of that group. Because of this, the group number was changed to 0. In the rest of the periodic table, the number of the group is the same as the number of outer shell electrons in the atoms of that group. Because of this, the group number was changed to 0. So, is that saying that helium doesn't react at all? Because it has none in the outer shell. Helium reactions. It's a very low and it's monatomic. Yeah, one atom. It's small and extremely light and is the least reactive of all elements. It doesn't react with any elements. Are there any other elements or ions? So no helium-bearing minerals in nature. Wow. Yikes. Okay, I did not know that. That is awesome to know. Okay, so the relative atomic mass of each element shown in the data book is calculated from the masses of all the isotopes of an element, taking into account the percentage proportion of each. There are 2 isotopes of chlorine. Since the relative atomic mass of chlorine is 35.5, chlorine 35 must be more abundant because its mass is closer to the relative atomic mass. Okay, cool. What did I just click on? Move on to video. Let's have a look.
Atoms are the building blocks of all matter in the universe. But atoms are not the smallest form of matter. They're made from even smaller subatomic particles. Helium is the second most basic element. It contains just 2 protons, 2 neutrons, and 2 electrons. At the center of an atom is a nucleus containing protons and neutrons. Electrons are arranged around the nucleus in energy levels, or shells, each holding different numbers of electrons. Neutrons are neutral. Protons have a relative charge of +1, while electrons have a relative charge of -1. Each electron shell has a maximum number it can hold. The first shell can hold 2 electrons and is closest to the nucleus. The second shell can hold 8, and the third shell can also hold 8. Magnesium
Wait, what was
shell
that again?
can hold 2 electrons
288.
and is closest to the nucleus. The second shell can hold 8, and the third shell can also hold 8. Magnesium has an atomic number of 12.
So
It
12
has 12
protons,
protons.
12
Because the number
electrons.
of protons doesn't change, it can be used as an indication of how many electrons are present. The total number of electrons in an atom is always the same as the number of protons in the nucleus.
And the mass would
This
define if
means
it's a neutron.
atoms have no overall electrical charge. The number of protons in an atom is called its atomic number, also called the proton number. The number of protons decides which element the atom is. Atoms are arranged in the periodic table in order of increasing atomic number. The atomic mass, or mass number, of an atom is the total number of protons and neutrons it contains. Nuclide notation shows the symbol of the element, in this case lithium. The atomic number at the bottom left shows the number of protons and therefore the number.
Okay, so this has 3 protons, 3 electrons, but that's 7 take away 3 is the 4, so it's going to have 4 neutrons.
Of electrons, in this case 3. The mass number at the top left shows the number of protons and neutrons added together. The mass number is 7, and the number of protons is 3, so there are 4 neutrons.
You.
Isotopes are different forms of the same element. Each form will contain the same number of protons, but a different number of neutrons, which means they will each have a different atomic mass.
I see.
Chlorine has a relative atomic mass of 35.
So it's 35.5 take away 17 will equal the neutrons. They're going to talk about the isotope.
In
Oh, I see.
Chlorine 35 has 17 protons and 18 neutrons and occurs about 75% of the time. Chlorine 37 has 17 protons and 20 neutrons and occurs about 25% of the time. Relative atomic mass is an average based on the proportion of different isotopes. Relative atomic mass equals 75 divided by 100 multiplied by 35 plus 25 divided by 100 multiplied by 37 equals 35.5.
Hmm. Okay, that makes a lot of sense. That's brilliant. What a great video. Heck yeah. That's awesome. Move on to test. Let's do it. So what is the center of an atom called? It is the nucleus. What is the charge of an electron? Electron has no charge. No, it is a electron is the negative charge. Which of the three subatomic particles is the lightest? The electrons. If atoms contain charged particles, why do they not have a charge? They contain the same number of protons as electrons. What is the atomic number of an atom equal to the number of protons? Number of protons and neutrons. Okay, where are the electrons inside an atom? The electrons are in the nucleus. They are arranged in energy levels. The electrons are spread equally throughout the atom. Which elements have similar chemical properties? Elements in the same period of the periodic table. Um, ha! I was going to say groups, so I guess elements with the same number of electrons in their outer energy level would make them have similar properties, so that makes sense. Elements with similar mass numbers. How many neutrons does this atom of carbon have? That's 14 take away 6 is going to be... wait, how many neutrons does this atom of carbon have? So it's going to be 8. 14 take away 6, yeah. As I said, my maths is terrible. What are isotopes? Compounds with the same molecular formulae but different structural formulae. Atoms with the same mass number but different atomic number. No. Atoms with the same number of protons but a different number of neutrons. Yep. Hydrogen has 3 isotopes and a relative atomic mass of 1.0079. Which isotope is the most abundant? Hydrogen has 3 isotopes and a relative atomic mass of 1.0079. Which isotope is the most abundant? Hydrogen with atomic mass of 1, 2 or 3. Oh no, I don't think I understood that video so well. I have to take a guess here. Let's say the most abundant. So it was saying that it was a percentage proportion. So it's going to be the one with 1. Let's see what I've got. Let's see, I reckon I did get it right. Okay, cool. Relative mass takes into account the proportion of each element. Nice, I got them all right. Ha! Let's go back to school, guys. Yeah. Nice, that's awesome. So I think I understand the periodic table a lot better now, actually. That has been really, really helpful. I wonder if I should stop here. How long have I been on? Let's see. Yeah, I don't want to exhaust myself too much. So I'm going to stop there. And maybe that was actually helpful to watch as well. That wasn't such a bad one because I actually learned something tangible. I think what I'm going to do is keep a picture of this as a reminder of episode 6. Oh, was this 5 or 6? Episode 6. And what we're going to do is continue with this actually, because this is really the fundamental thing I need to know. Oops. before I start trying to automate stuff and do pipetting and all that crap. I need to understand this stuff properly. So I will see you in the next episode of Dragon Ball Z. Bye for now.